bioenergetics has basically become a very hot topic because we've been thinking about how to utilize biological systems to make energy in regards to removing ourselves from the reliance on fossil fuels. So we have our interaction with our heterotrophs and our autotrophs to give us the capacity to transfer energy. Like, we like eating a piece of steak, we like eating certain plant materials, and they all give us particular energies. And energies is seen in the sense of the situation of moving electrons from one system to another, but then also utilizing the commonality of proton movements also. And with those proton movements and those electron movements, we can get rearrangement of bonds and allow us to store those particular energies, such as electrons and protons. There's always an equal movement of electrons and protons in regards to changing molecules. So here we have an example of lactic acid or lactate and pyruvate, and we're going to come to know these two structures a little later on. But what we see is a simple transformation from lactic acid to pyruvic acid or pyruvate by the addition of 2 electrons and 2 protons. Ultimately, we'll see a structural change in lactic acid to produce pyruvate. But we have then pyruvate as a store of electrons, and we can recuperate those electrons by reversing the reaction using enzymes to basically remove those electrons and bring it back to lactic acid. So again, here we are getting one's in to produce pyruvate, one's out to produce pyruvate. So we have 4 types of chemical reactions we are going to look at, and these are the oxidation reduction reactions. And here we must have both present to do the job. So we have a example here where we have a dehydrogenation reaction combining with an oxidation reaction to cause the release of energy when we look at the oxidation of carbohydrates. Now, we might see both homolytic and heterolytic cleavages occurring in these particular molecules, which provide a level of instability. But we also see this in the same reaction system when we look at reactions that make and break bonds in regards to whether we are going through anabolic or catabolic metabolism, where we're basically making and breaking bonds to make things smaller through the world of Gibbs free energy and entropy. So we have these carboanions and carbocations, again, homolytic and heterolytic cleavages. But again, these guys are a little bit problematic. We're going to have to be able to mop these up very quickly to ensure that their electron transfer is appropriate and safely done. Because if we cannot transfer electrons safely, we're going to have some very serious problems that we'll see in later lectures. We also have this issue of internal rearrangement of particular bonds, where we're going to see isomerization and even elimination in regards to certain chemical functionalities. Now, some of those chemical functionalities can also go through what we call group transfers, where we might remove a CH3 group from one molecule and form a double bond on that molecule, and then transfer that particular CH3 group to another molecule at the expense of a double bond. So again, we're going to have to think about this particularly in regards to how we transfer different types of functional groups. Our final one, the free radical reactions, these are highly dangerous for us in regards to, but essential in regards to producing radical species that are highly reactive. And we want to keep those in very close proximity and contained, because they're going to react with all types of things. But we want to be very specific how we produce those and how we actually then regulate and modulate those particular reactions, as we'll see a little later on. So when we think about our carbon constituent, we have the capacity to be a nucleophile, an electrophile, where the electrophile is going to be receiving electrons and the nucleophile is going to be being the donor of electrons. So depending really who we're sharing our electrons with that particular carbon moiety, what for chemical functionality, with the hydrogen, oxygen, sulfur, etc. And so it's going to depend whether it becomes a donor or acceptor. So we're now on page 495. So we should have covered nearly 500 pages. We skipped 2 chapters, but basically have undertaken basically a whole load of reading. So hopefully you're keeping up with the reading. And if you need revision and to keep up, hopefully the spring break will be well utilized to do that. So we're on page 495 and discussing up to 527, which is the opening to bioenergetics and our metabolic pathways, which will be the focus of the remaining part of this course. So let's have a look at bioenergetics specifically, where it's the relationship, a quantitative relationship of energy and the conversion of that energy within a biological system. Remember, we have closed biological systems and open biological systems. So go back to some of your definitions from the previous lectures. But they all obey the laws of thermodynamics. So again, we have to make sure that we can account for all the bits and pieces to make sure we are at a consistency with those particular laws. So we have the law of conservation and energy in regards to making and breaking bonds, and there has to be an equal and opposite reaction. We also have the entropy in regards to the the universal increase of energy during a chemical reaction or process, because we're trying to make a larger molecule, bringing it down to smaller constituents so we can get no more energy out of it. So if you think about what we actually do when we think about carbohydrate metabolism, the end product is when we have those 5 and 6 carbon constituents and all those other up to 7, 8, 9, 10 carbon constituents that we've studied from our carbohydrate chemistry. When we look at the complete oxidation of those particular constituents, it's going to be water and carbon dioxide that are going to be the final products. So you think about, let's say, the structure of glucose. We are breaking every single bond slowly, one by one, until we are producing carbon dioxide and molecular water. So again, we've got to keep that in mind in regards to our catabolic metabolism. So we already know delta G and Gibbs free energy. We already know we can calculate the change in the delta G energy from the equilibrium constant in regards to delta G equals the room temperature in Kelvin with the gas constant with the log, the natural log with the KEQ component, where the KEQ equals the products divided by the reactants. So we recall specifically, and this is really important to understand, that when we have a delta G in the negative, that the reaction is exergonic, and it's a favorable reaction to move forward. When it is in the positive, it's an endergonic reaction, and therefore we're going to have to basically provide energy to move forward. It's not a favorable reaction, and that's where we get those particular coupled reactions occurring. We have then the entropy and entropy, where entropy is making and breaking those chemical bonds, and entropy is the randomness and disorder, meaning getting to the smallest molecules possible in regards to both conserving energy and extrapolating energy as we break those individual bonds to make something that is going to be stable. Carbon dioxide and water are stable in regards to not being radicals, not having group transfer capacities, but they can also be utilized, though, still as biochemical agents for other biochemical reactions, as we've seen with carbon dioxide and molecular water playing a role in various biological reactions. So in this case, we see importantly that delta G is a function of our products and our reactants. And think about these products and reactants in the sense of our enzymes. Remember, we are taking a individual substrate, which could be a reactant, and basically producing a product, which is the product. So again, we now bring it to the focus of enzymes. So again, keep that in mind, because that's going to be a very important feature. So we also have the standard energy change, delta G prime, where basically we're looking at the KEQ in regards to equilibrium. And remember, we have a reaction, A plus B equals C plus D, and at equilibria, the forward rate will equal the reverse rate. And we utilize a standard situation where at standard pressure and temperature at 25 degrees Celsius, 1 atmosphere, and that the products and reactants are at 1 molar concentration. So this is the standard system that you might have seen in your chemistry. And therefore, we can produce a simple equation from the KEQ to the Ka in regards to the reactants divided by, the products divided by the reactants. But keep in mind again the issue of putting these in an enzymological feature in regards to the individual reactions. So when we see these individual reactions start to summate, the products from one reaction are going to be the new substrates for the next reaction, and vice versa as they go down the chain. So keep that in mind. We also have this issue regarding pH and also the water concentration of 55.5 moles and the standard transformational constant. So again, I bring this to your attention with the KEQ component now added to the delta G prime 0, where we're going to see this particular number either being greater or larger than 0, playing a key role whether we're going to see a negative, 0, or positive component in delta G. When we see a positive delta G, we're going to see the reaction proceeding in the reverse direction. If we see a negative delta G, we're going to see basically the reaction producing in the forward direction with a matched KEQ number here, which is going to be greater than 1. If this is 0, we're going to see a delta G in 0, and then, if this is 1, I should say, this is 1, the delta G is going to be 0, and therefore we're at equilibrium. So we're going to see this delta G free energy and a change of the delta G prime 0 is a standard measurement in our biological systems. But again, this becomes extremely important to understand, and I'm recapping this for obvious reasons because it's going to be utilized in the rest of the semester. So here we have our first biochemical reaction, and I've put it in very simplistic terms. And you need to be able to understand what's occurring at every individual reaction that we're going to look at in these types of terms, because we're going to look at a glucose 1-phosphate and glucose 6-phosphate production. I haven't shown you the mechanism. I haven't shown you the consuming components, such as, there's going to be some enzyme here that's going to transfer this phosphate from glucose position number 1 to glucose position number 6. So we're going to look at the KEQ and the delta G prime 0 in the sense of energy requirements. So we start with 20 millimolar of glucose 6-phosphate at 25 degrees Celsius pH, and we get to equilibrium with the enzymes appropriate. We measure then importantly how much of the products we have and how much of the reactants we have left over. So a very simple transition in regards to the transfer of this phosphate within glucose molecule. You should be able to draw the glucose molecule with the phosphate and identify the positions number 1 and number 6, as we've already indicated. So in this case, with glucose 6-phosphate, we have our end product at 19 millimole compared to the glucose 1-phosphate, where we have 1 millimole. So we can calculate the KEQ quite easily, which is going to be the reactants, the products divided by the reactants. So again, the glucose 6-phosphate, which is 19 millimole, with the glucose 1-phosphate, which is 1 millimole, which is 19. The KEQ is 19. Now, this doesn't tell us anything about the energy requirement until we use this in the equation, the KEQ, to produce the delta G prime 0. So when we do all the math behind this, we find we get negative 17.3 kilojoules per mole. So from this reaction, we are going to have a capacity to release energy at 7.3 kilojoules per mole, because it's a negative value, the negative delta G prime 0. But if we want to counter-react this reaction and force the equilibria, not on, because at the moment the equilibria is fancying and favoring this side because of the negative delta G going this way. But if we want to push this in the reverse, we are going to have to use the energy input of positive 17.3 kilojoules per mole to bring the change where we can see 19 millimoles of glucose 1-phosphate and 1 millimole of glucose 6-phosphate. So if we need to reverse this, we just reverse the sign in regards to being positive or negative. Now, so let's look at the issue of the reaction itself between delta G and delta G prime 0. And again, we've seen this equation before. So the spontaneity of the reaction is the value of the delta G component, not that of the delta G prime 0. So we can rearrange this equation and see what that particular value is going to be in regards to will it move forward or not, given the analysis at equilibrium. Okay. So let's have a look at what's going to occur energetically when we break this particular reaction down or another reaction down in regards to the additive components of single half reactions. So we have a delta G prime 0, 3, which is actually the summation of two individual delta G prime 0 reactions. But because they have a overall component of reaction, we look at the half reactions and give us an understanding, importantly, what's going on. But some of these half reactions we only know in one direction. And as I've told you before, if we have to understand them in the opposite direction, we need to change the signage of the amount of delta G energy they're providing. So here we have a reaction of phosphoenol pyruvate, we'll study this reaction shortly, with ADP. We have an enzyme that does the work, and in this case, it's going to rearrange the phosphoenol pyruvate to produce pyruvate, and then allow us to phosphorylate that ADP to produce ATP. So this is the overall reaction, but we can break this down into two-step reactions. The degradation of ATP to produce ADP and inorganic phosphate. When we get this particular reaction, we get negative 30.5 kilojoules per mole, so a lot of energy. But we get more energy when we see phosphoenol pyruvate being degraded to pyruvate and inorganic phosphate. We get negative 61.9 kilojoules per mole. But the issue is, we look at our particular reaction number one, it's not in the right orientation because it's indicating that ATP to ADP and PI is negative 30.5 kilojoules per mole. That's why it's got this little red arrow here. Because if we look at our overall reaction, we're actually taking ADP and making ATP. So we have to reverse this particular guy, and therefore we need to reverse the equation here, the signage on the delta G requirement. So this now becomes, for this overall reaction, becomes positive 30.5 kilojoules per mole plus negative 61 kilojoules per mole. We're still in the benefit of producing energy at negative 31 kilojoules per mole. So the reaction is the sum of reactions 1 and 2, the two half reactions, because the reaction number 1 needs to be reversed because we can't tell the energy from the ADPPI to ATP, but we can tell it from ATP degradation to make ADP and PI. And because we know the previous slide, we can basically just reverse the energy signage to give us the proper delta G. And that's why we get negative 0.31.4 kilojoules when we cause the degradation of this per mole. So the reverse of the reaction, we just change the signage to give us, this case, a positive delta G requirement. So therefore, this particular reaction to produce ADP and make ATP is our endothermic reaction. Here's our exothermic reaction. We're going to couple those two together to produce a reaction that's still going to produce energy, and our products, pyruvate and ATP, with minus 31.4 kilojoules per mole left over, which we can then add to another reaction to allow that reaction to move forward. So free energy released during the reaction determines the energetic compounds and the progression of the reaction. So in this case, because we have a stimulating balance in regards to surplus energy, this reaction overall will move forward to produce pyruvate and ATP. But again, I stress, if you want to go to the reverse and consume ATP and consume pyruvate to produce phosphoenol pyruvate and resulting ADP, the overall reaction will then change its philosophy and become positive because you are now changing this guy in the opposite direction, and this guy will become then positive. Okay, a very unfavorable reaction in that particular opposite direction. So hopefully you're understanding that particular component. If we have a look, I just want to stop it here. If you have a look at some of the free energy, and we are going to actually talk about every one of these single reactions in regards to the remainder of this course. Look at the amount of energy that is occurring in regards to We use kilojoules per mole. Some people use kilocalories in the old form, but the delta G requirement indicates clearly there are some energetic reactions that are more favorable than others, and that some are going to release more energy in regards to their degradation. So let's have a look at the simple issue of ATP and water hydrolysis and having that ADP and PI. We already saw it, negative 30.5 kilojoules per mole. When we even take ATP and hydrolyze it to make AMP and pyrophosphate, we get even more energy in regards to that negative 45 kilojoules per mole. Because what we see clearly is that we can take that PPI, that inorganic pyrophosphate, hydrolyze it again, and produce two molecules inorganic phosphate, which is negative 19.2 kilojoules per mole. We're going to go through a whole lot of these particular biological reactions in regards to what we're going to see when we look at our metabolic pathways, and I'll continue this after spring break. So we've got an introduction again to recap our Gibbs free energy, our KEQs, our delta G prime zeros, our delta Gs, our endo and exothermic reactions, our reactions of coupled nature, and now importantly, this type of information in regards to looking at simple equations and looking at the half equations in regards to the energy consequences and whether that energy is going to allow that reaction to move forward or does it need to be coupled with another negative delta G prime zero reaction to supplement that particular system to allow it to actually do its particular job, as well as now thinking about if you're reversing the reaction, what are the consequences in regards to the individual half equations and how we have to rearrange those half equations to get the appropriate signage in regards to the delta G prime zero for those half reactions. So hopefully you've got that going to be mastering that because it'll be on the exam, it's on the homework. Okay, so I will leave that to you now. Have a great spring break. Be safe.